Okay. Hi, my name is Brendan Madden. I'm the CEO of Tom Sawyer Software in Berkeley, California. And I'm going to be giving a talk on graph visualization and analysis technology. A little bit of my background. Actually, I work in graph technology since 1985, almost 30 years. I started doing network layout at IBM Watson Research Center, and then built graph-based products even back then. And then I worked at Santa Teresa Lab in 80 cycle drawing schema and query results. And so I built two automatic layout systems, which were graph layout systems, before starting Tom Sawyer Software in '92. So we were probably the first American graph visualization company. And we're well known in the software industry. Yeah, my background is in physics and applied physics, which is not a problem. Some of our, we're in the software company space, and we've been moving into the enterprise over time. So we have a lot of clients. So I'll just continue. We have, so we began with an experience in graph-based data structures, and then we were doing graph layout technology, which is taking the structural information and topological information and calculating diagrams automatically. And so first we began with graph layout problems, and there's different domains like directed and flow-oriented data, network-oriented data, schematic-oriented data, and each of them demands different directions in the layout technology. So we started with layout technology, and then you get into problems of nesting, nested drawings, labeled drawings, incremental drawings, so drawings that change over time, and you want to preserve the user's perspective. Then we moved into like visualization platforms, which can be embedded into applications. So that was in the mid-90s. And then in the early 2000s, we moved into graph analysis products. So, and graph analysis is about clusters, traversals, pathfinding, reachability, root cause, SNA, social network analysis, and network flow algorithms. So basically it went from layout to visualization to analysis. So what I'm going to be presenting, around the middle of the 2000s, we started to generalize the problem. We said they work with types of data, they want to know where the data is coming from, and they want to know the views of the data that they want. So we built a configurable platform, getting away from all the heavy API programming, moving towards configuration so people could build applications quickly and configure them and change them in the field, like during POCs, doing services engagements, and this kind of thing. So this is an example where we actually this is a commodity flow example where we originally started with Excel-based data, just as we got the data set in Excel. And we built an application that worked with Excel, and the drawings would take 2 or 3 minutes to come up because of processing the Excel data sheets. Then we exported from Excel in CSV format and then imported into Neo4j. And then it goes down to more or less being instantaneous. So what we have here is with Tom Sawyer, you can define, we have integrator definition and view definition. Everything we do is rule-driven and configuration-driven. So you can write sophisticated rules to go, you can have filters, and you can have rule-driven views of data. So in this one, this was we have this tree control drives certain data. So we have the states in the United States, and we have different commodity types. So I'm saying, well, maybe I'm interested in the auto industry. So I'm going to click on Michigan is probably interesting for auto. Ohio, maybe for tires and other manufacturing out of Ohio, and maybe Texas. They have a lot of factories in Texas. And then I might say, so I click the right buttons. I might, in what commodities am I interested in? I could say, base metals, different types of base metals, maybe electronic components. So what I'm doing here, underneath this, we have cipher queries. So we have you know, we have a Neo Cipher data integration, and we can define, in our design technology, we can define queries and we can have more than one integrator. We have federated integration. So for different aspects of an app, we can have multiple query definitions. And one might be the initial load, another one might be an incremental load. So we can do sequenced data integration. So I'm going to run a query now. I'm querying. So Tom Sawyer has multiple synchronized views of data. So here I've selected the information. I've got the states showing up in a data-driven tree control. So I'm seeing the states here on the left. I can see the areas within the states that are of interest, where materials are, you know, manufactured. And similarly, I can see, you know, the commodities. So Tom Sawyer has tables, trees, diagrams or drawings, charts, maps, and property inspectors. And what we do is provide a synchronized, model-driven views of data. So if you select on one view, it synchronizes and selects and focuses in on all the other views simultaneously. So here we have a data-driven chart view at the bottom, and I could see, okay, Ohio has a lot of imports in, you know, I think that's millions of, you know, so it's millions, so a lot of imports, a lot of exports. Michigan, similarly, in auto parts, you know, an auto manufacturer, a lot of imports, a lot of exports, and similarly, Texas. So then you might say, well, that's nice. Maybe could you show it to me on a map? So maybe I'll show you a network on a map. It's a little bit, so here I'm showing data-driven Google Maps views. So this is just going, and we also have an OpenStreetMap project where we'll be able to do it if you don't want to have a public service access. So for instance, that's showing the commodity information flowing on a map. And then here's one showing the directed graph. It's a little bit light, but it's a directed graph of all the commodity flows, you know, with labels that say how much, you know, how much money is flowing, you know, in commodity value. So, for instance, if I were to say, okay, let me click in on Cleveland area, you know, I could see. You see, I have rotated labels automatically placed on a directed drawing there. And you could say, so for instance, then if I came over here and I clicked on, you know, Cleveland, if I go over here to, you know, there I am synchronized, like I was saying, on the other maps. So that's like going, you know, keeping coordination between different views of information. And then you might say, so that's a directed, flow-oriented drawing, which might be in a dependency graph, a supply chain, a logistical application, you know, any kind of a software engineering application would have flows. But then you might say, well, let me look at that differently. Maybe I'd like an orthogonal schematic representation of that. So now what you see, now what you see is an orthogonal schematic with overlap-free labeling. So if I were to zoom in on a section of this, I can see, if you see, what you have is precise clipping to the geometry of the defined graphical specification of the images. You have labels that are non-overlapping, and you can, you know, navigate the drawing. Like I could, for instance, let's do some link navigation around this area of Texas. So I can like go around the links, like for instance, like that, and say, oops, sorry. So that maybe this link is of interest to me, and it takes me to Houston. Or you might say, in a data-driven, could you maybe group, show me this data again, but organized by state? Can you group it by state for me? So Tom Sawyer has, as I say, it's rule-driven. So rule-driven and data-driven visualization. So here I'm going to say group that by state. And then I'm going to come in here and, for instance, collapse it all down, do an incremental animated drawing of that schematic, and it's showing the broad financial flows between the states. And you could say, well, that's nice. Now, maybe you could say expand it all. Now I've got a nested, automatically laid out orthogonal schematic. What you're seeing is drawings that I can read at any level of detail. You know, with not, you know, you don't see edges on top of each other. You don't see labels overlapping labels. So so we have labeling, routing, incremental drawing, and full dynamic navigation environment. So, or I could say, for instance, I really want to, so this is Texas, and I see a tooltip showing Texas. Now I say, maybe I'll just drill down into Texas. I only want to see the flows that are fully contained within Texas right now. And I can go up and down through, so there's a lot of need for hierarchy. So graphs are wonderful, but you need to be able to do attribute-based grouping, nesting, and go up and down, like in data center projects and all sorts of applications. You need hierarchy, enterprise applications, enterprise architecture. You need to go up and down through this data, and it takes years and years to to do the layout, the visualization technology. So we can give people .NET. We have a full .NET architecture, a full Java architecture, and in both sides you can go desktop or web. So we give people a configuration, and you do configuration of all your data, and then so I'll show another example. So this is our Tom Sawyer Perspectives environment. So what we have is, so we do a design, preview, a round trip process. So we used to do this all, we had many experience for many years where customers would write 10,000 lines of API code, like network management company, like a Cisco or some Israeli networking company would write 10,000 or 20,000 lines of Tom Sawyer code. And the patterns of integration that customers had was over and over. It was really how to go from their data model to ours. And so they had to do all this configuration, defining the graphics, extracting the entities, extracting the relationships, and then sending them into our views of data. So we started to build all those pipelines back and forth. So it really became what kind of data, where's the data coming from, and the views. And what we decided to do was say, let's build that into a configuration environment. So here you see, this is like a network editing project. You have the idea of like schema. We have schema and schema rich or schema less capability. And you can see like several data integration sources. So I'm not going to worry about the data integration, but then I can have like what we call drawing templates, which give me a way to visually define my graphics. So we have level of detail graphics. So as you zoom in and zoom out, you can show less or more detail as nodes zoom in and out, or links as well. So these are examples of ways to see data-driven presentation. So for instance, here I'm saying host name in that data. Maybe I could change that to IP address for the title or some other property in my data model. And I'm saying in this application, I want 3 drawing views, 2 tree controls, 2 tables, an inspector, and some search. So for instance, you see like in a network map definition, you could say, well, people need, just in my application, I want to say, what are my toolbars? What are my rules to generate that view of the data? So I have graph-based data. We have both table data models, and we have upcoming graph-based data models, which will go directly from Neo right into schema, direct loading from Neo into a data model, and then rule-based view generation. So if I was to just preview this, this is an intermediate preview step, but you see, so for instance, if I expand all, I could group by location and by like type here. So for instance, if I do the layout on this, I get like orthogonal animated schematic, maybe a directed graph. I could synchronize, in on particular properties. So everywhere I view, you see all the views are dynamically keeping up to date. So this is just an example. So that's like the devices. And if I were, for instance, to zoom out, you see or zoom in, I'm going to show more information as graphical. You could do multiple attributes that are all data-driven and rule-driven from data to graphics on your nodes and your links and your, this kind of thing. And so you see overviews. they're tight-fit overviews that you can navigate around, and features like this. So you see a device table where I can say these are my entities I want to show, or my nodes, and then these are the attributes I want to show, and for each attribute I have a renderer. I can define, so I can define toolbars, custom renderers, custom programming, and everything. So the idea is people take the result of this preview step and then they embed it into their larger, so it's really, it's still an SDK. It's designed to be integrated into, corporate web apps or production software company products. So the idea is you can say, I want to do a desktop app or a web app. So for instance, you see this particular visual definition, you see this toolbars like save as image, print setup, print, this kind of thing. So I could say in the designer, well, I don't really want save as image anymore, and I don't want print setup, and I don't want preview. Just let me preview it again as an image map web application. So now you see the toolbars have just changed. So I didn't have, so what we do, the output of this is an XML definition. So what that allows, instead of us having to code that, we can define a configuration and then it gets loaded when the app runs. So what we do is we allow people to configure like really quickly without having to go back to IT to write code. So people can work that way. So that's an example of a network editor. So I'd like to show, I'm doing okay for time. So I'm going to open a network project. So I'm going to say, maybe I want to look at social data like companies and directors and officers. So it's an example of like a, entity management or corporate governance kind of application or securities and exchange application. So here you see this one, we have company drawing and social network drawing and several tree controls and charts. And so if I was to just preview that, so I have network representation of the directors and officer relations coming from the data source. And you could see like that's a symmetric layout. This is what we call a circular, so it's a clustered. So we cluster and analyze the links between nodes, and we do dynamic, very fast, like ratio cut partitioning, and then we do. So you see, we make a graph of clusters, and then we also do, like a relaxed spring embedding within the particular clusters. So that's an example of a circular layout drawing. That's a sample of the same data as this is. So this is an example of the same data as a schematic representation. So this is really useful. And so you can see they're very clean. You can follow. And you might say, well, gee, that's really nice. I've got people and companies. But actually, what's really important is really who knows who. It's fine. I care about the companies at some point of view. But maybe I care more about the people who know each other rather than who they work with today. So we have rule-driven view definition. So we can have particular properties in the data that we use. We write rules, and we dynamically generate graphs, which become the input to the drawing system. So for instance, I might say, well, I want to write a rule if I have people, maybe two people work for the same company or they're associated with the same company. That means just make a link between them and the data in a graph structure. So that's what we would call a social network, and then that's what that view. So that's the social network of that company network. So it's a different, but what's interesting is that social network was not in the data. It was not defined. But through the use of rules, we dynamically generated graphs. And then we could commit that stuff maybe back to Neo, and then work in a, so we actually inferred graphs from data that didn't have that representation. So the rule-based and data-driven approaches to generate graphs is very powerful, and it's not, a lot of times the relationships are not explicit. They're just you have columns of data. Maybe one column is manager ID, person's name and person ID and manager ID. So that's, and you might say on this particular view, I care about inferring. I can just because on a data-driven manner infer that relationship. So then you might say, well, that's nice. Maybe that's too much information still. why don't I filter out all nodes of degree 1? And so I'll go ahead and say, okay, just show me, and there are bidirectional links in between some of these. So if I go, show me everybody, so that'll filter out. So as I was saying, is all views are synchronized and all actions are model actions. So I'm setting a filter on the view, all the views. So that's why this view dynamically updated over here. And then I could say, well, let's incrementally lay that out. And it gives me a new clean representation. Now I'll go to the social network, which should be changed as well because I've filtered here. And that's what you'll see over here. Now there's much less data in the social network. I'll lay it out again. And then maybe I want to perform some analysis now on that more, so I cared only about people of higher connection. Now I might say, well, let's run some SNA on this network. And so here's an example of, okay, that's like between this centrality. So that's an example of an algorithm that says score people by the number of paths they are on across all the paths in the network. So what you get, and then we defined a synchronized centrality view over here. And I get those people normalized between 0 and 100. So that's a rule-driven configured view sorted by their score. And I could say, well, that's Marshall. So now this would give me a way to do like fraud detection or some law enforcement work or some intelligence work, whatever is of interest, and similarly, so here's this Jerome. So that's a schematic. And you can say, oh, that's interesting. The orthogonal view gave me, it's interesting, I have this little subgroup up here that is all connected to this Jerome. So now I know I have some information that I should, those are his pals. And so then I maybe go back, let's go back and see what companies. Now I go back to the other view and I can look around that person and see, well, who does that person really affiliated with? And so you can, it's really powerful to do dynamic perspectives of, multiple perspectives of view. So we started with tables and trees and drawings, and then and inspectors, and we've moved into charts and maps. And it's, so what's nice is you can define these applications just by, in a design environment, you just create views and write rules. So you can, and then it's all bound into an XML file that then gets loaded in the web app that you're using. So for instance, that's a clustering on the data. If I was to say, this is another one, like between start and finish, how many disjoint paths that like non-edge, the edges are not reused, to show me all the paths between start and finish that where one edge or one relationship is not reused. So if I run this, it tells me, oh, there are 3 paths between the start and the finish in an edge disjoint manner. That's relation. So if I said, now the nodes can't be reused, and I ran it again, okay, well that node that node is forcing, now you say there's only 2 paths because this path can't be used because it's already taken up by the other path. So that's an example of, or you might say I'm doing some, why am I having a manufacturing problem? So root cause is another graph algorithm. You could say I've got these effects in a network. How do what might be the causes of those event logs filling up, or there was problems down the line. So I could run like root cause, and this tells me, oh, I have 14 nodes in that data set that I should investigate. So that gives people like a systematic way to go about working on a problem. And or you could say like in like route finding applications, I need to show me between start and finish. And I have these costs and capacities on the nodes and links, or I could say, well, let me iterate the paths from shortest to longest would be an example. So it's like, what's the shortest way to walk between 2 places, and you get 3 paths from Google. So here this one tells me there are 24 paths between start and finish, and I'm sorting them from shortest to longest, and so you can see I can iterate them and they're getting longer, through the data. So we have a long experience in graph analysis and this kind of thing. Yeah, thank you.